Now we study forward velocity. Okay. So this is a forward vector for a particle moving with velocity v. Let's take the derivative with respect to time. This is moving with a constant velocity. So if I take the derivative with respect to t, then what I find is a cv. I'm hoping to have this one to be full velocity. If it were a full velocity or full vector, if I square this should be invariant under Lorentz transformation. Let's square this. Then the result is c squared minus v squared. Okay? This is not invariant under Lorentz transformation. Under Lorentz transformation, this velocity must vary. Sometimes it is at rest. For example, x prime mu equals c tau 0. This is the description of the time and position for a particle, the same particle, seen by the same particle. I mean, sitting down on the particle, then only time is going. Then, if I take the derivative with respect to the same thing, and remember, t equals gamma tau. Right? Do you think this is it looks like they are invariant. Are you allowed to say they are invariant? Yes or no?
No.
Why?
Gamma is not invariant on Lorentz transform.
Right. So, the good way to write, what I mean is the right hand side is not invariant. It is subject, it looks, they are invariant between them. However, because it has the velocity dependence. Velocity dependence. This velocity is arbitrary. This is depending on the frame. So the right hand side must be independent of frame. And even though these two are the same, that does not mean this expression is independent of frame. Okay? So, our question is, how can I construct a full vector that is related to the time derivative? It's good to start from this part. Let me put 1, 1. Space-time position of event 1 and space-time position of event 2. So this star is moving. This is event 1, event 2, seen by somebody at frame S and seen by somebody in S prime. Okay? Because their relative velocity v, this is fixed. We have the same Lorentz transformation method, right?
Funny.
Unprime. Subtract that. Then we can factorize. So let us call this guy to be delta. Change in space-time position. This means the difference of this four displacement is still A4 vector. They follow the same transformation rule. If I want to take the time derivative, I have to preserve this relationship. I have to make use of a factor that is related to time that is independent of Lorentz transformation. The only times that is independent of frame is proper time. Then they preserve the relation for the Lorentz transformation. The reason why this relationship was not satisfied by t is that t varies depending on the frame. So I want to use the time that is independent of frame so that this Lorentz transformation is still valid. Then if we define this to be u for velocity in this frame, prime frame, and this is, then they must be invariant on the Lorentz transformation. And what is this value? The simple choice is choose this rest frame. And in the rest frame, x prime mu equals c tau 0. This particle is not moving. And in this frame, I can still make use of proper time. This time is proper time. So I make use of proper time to take the derivative. And this is u mu in the rest frame. If I square this, the value is independent of velocity, so independent of observer. Okay? Independent of observer. So we call this one to be full velocity. Then what happens to the full velocity in general frame? That's our concern. In general frame, this is a CT and VT, right? In comparison with this, the full velocity in this frame, u prime u, is C dt over d tau, V dt over d tau. But we remember, in comparison with the rest frame, dt equals gamma d tau, time dilation. So gamma is factored out. Gamma c v gamma. Right? So u0 equals gamma c prime, and u vector equals gamma v. So for velocity, the spatial part of the for velocity is dilated in comparison with the velocity, which is actually measured by us. What we measure for the velocity of a moving particle is, I cannot use proper time to measure the particle's motion. I must use the time that has been dilated. Okay? This is time dilation effect appears here. Before we take the derivative, we could have used the C gamma tau and V gamma tau, right? Already. And take the time derivative with respect to the proper time, then V gamma, C gamma. Right? But we still do not know what this Zeros component really means yet. Next step is for momentum. In an analogous way to derive the forward velocity, we would like to construct a forward momentum that is related to our usual momentum. When we obtain this forward velocity, what we did is take the difference of the displacement, which is still a forward vector, but in the denominator we multiplied a scalar, Lorentz scalar. Tau is defined to be right? I want to define for momentum P mu. If I want to multiply mass, I want to multiply some mass which is independent of frame. Still, we have not found the mass is changing, but as soon as we learn relativity, time has been dilated, so it's possible to have variable mass. We have to open. So let us assume mass can even change depending on the velocity. So let me put 0 to identify this to be rest mass. Mass that has been measured in the rest frame of the particle. Then, because it's a Lorentz invariant, this is 4 vector, Lorentz invariant scalar, so this should be a 4 vector. So it should be M0 C gamma and M0 V gamma. Right? Again, this is different from the real velocity we measure. This is different from the real velocity we measure. So But what is that? Mass 0 times gamma. Perhaps mass can vary. Mass can vary depending on the velocity, but we are not sure what really it is. And what is that? We don't know yet. So we would like to identify what this means. In the rest frame becomes M0C and 0 vector. So let us define this one to be P vector, and this is P0. And we would like to interpret the meaning of the zeroth component of the 4 vector P. All right. What is the force? Force is the time derivative of momentum. Okay? And this time should be dilated time. Dilated time, so gamma d tau. Right? Time derivative, but this guy is what? Derivative with respect to normal time, right? So what we have to do is just do the similar way. Gamma 0, M0 gamma, right? This is this. And M0 is assumed to be invariant under Lorentz transformation. This is the force. Okay. What happens to this force times velocity? What is that? This is F3 is power. Right? So let us simplify this. Power is M0. Why don't we make a total derivative? Subtracted by okay, dt. Okay, power is work divided by the time, right? Change in kinetic energy is the, if I do some work on this particle, it will produce a change in kinetic energy. Change in kinetic energy is actually integral of work, that is